Assalamu alaikum. My name is SM Jubai Sharka. I will present in the introduction part. So, as we know, brain tumor are a serious medical condition that can be life-threatening if not detected and treated early. Traditional radiologists manually analyze MRI scan, which is time-consuming and sometimes error-prone process. This create a need for more efficient and reliable solution, and that's where artificial intelligence come in. Our project aimed to automate the classification of brain tumor using convolutional neural network (CNNs), a powerful deep learning technique well suited for image analysis. CNN can automatically detect and learn visual features from MRI images, helping identify different tumor types. We use publicly available dataset from Kaggle, which include thousands of labeled MRI images categorized into four classes: glioma, meningioma, pituitary tumor, and no tumor. This dataset provide a solid foundation for training and testing our model. Through this project, we aim to support the medical field by providing a tool that can assist in faster, more accurate, and automate diagnosis, potentially improving patient care and treatment outcomes.
So we used CNN for multi-class brain tumor classification. It is chosen for its strength in detecting spatial patterns in medical images. It automatically learns features, so no manual feature engineering needed. The input size is 150 by 150 by 3 RGB MRI scans. The network includes three convolutional layers: ReLU, activations, and max pooling, followed by flattening dense layer 1 to 8 units, dropout and softmax output for 4 classes. Implementing details. So we built using Python with TensorFlow and Keras to run on Google Colab with the GPU. Model trained for 30 epochs using Adam Optimizer and categorical cross-entropy loss. Performance evaluated using classification metrics and visualized via confusion metrics.
Assalamualaikum warahmatullahi wabarakatuh. So I'll be presenting the demonstration of the code. Firstly is for importing the datasets into our Google Colab. So our current dataset is actually from Kaggle Hub. So we have to import Kaggle Hub to actually get the datasets from Kaggle into our Google Colab. Next, we have to install Open Datasets, which is a library that will allow us to access our dataset from Kaggle. And for our dataset, when we want to download our dataset, we have to ensure that you just put a random Kaggle username and Kaggle key, then it will start downloading and it will appear into your file browser, which is under Brain Tumor MRI datasets. Next, we have important libraries. We have a few libraries. Firstly, we have the OS, which is just to interact with the operating system, and then the Python imaging library, which is to open and manipulate and process image files. Next, we have NumPy, which is for to do any mathematical operations, and then Pandas for data manipulation and analysis. Then we have Matplotlib, which is to create data visualizations such as histograms, bar charts. And then Seaborn, which is visualization library based on Matplotlib. So it's just the same as Matplot. And then next we have Scikit. This one is to evaluate model performance. And then we have TensorFlow and Keras to help us with the AI model building. Next, we have the visualization random samples. This code will actually just generate the images that are from the dataset. And then, like we can see here. So I can just start playing, and it will actually show the images here. Next is the info of images, which is to show each classes that we have. We have pituitary, no tumor, and meningioma and glioma. So it's just going to tell you how many images are inside those folders and the average size of the images and also the channels. Then next we have the class distribution in datasets. This one is just to distribute the dataset according to the classes. And then we remove the corrupted images. This is part of where we clean our data and ensure that each images are can be easily used to train the AI model. So actually for the remove corrupted images, it is to actually segregate what is JPG, JPEG, and PNG from any other files that are located inside the dataset. But so far there are zero corrupted images. So next is the normalization, where we actually standardize every image and every color of the image to be the same. We rescale it to 1/255 to ensure that every image is every image is the same size and the same color, and it will be segregated into their own classes. Next is where we build the CNN. The CNN is the CNN that we use is sequential. Um, it's it's more of a layer type of CNN that we use. We can see it from this image to have a better visualization. Where firstly we have conv2d and batch normalization and max pooling 2D. So these three functions are considered as one convolution block. But every convolution block will have different number of filters. So for the first block, there will be 32 filters. Second block, there will be 64 filters, and the last block will be 128 filters. So the 32 filters means that it has 32 different scanners, meaning that they are trying to detect a unique pattern in the image. And then when it goes into 64, meaning it will detect much more complex patterns. And then when it goes into 128 filters, then it will try to detect any detailed features like the tumor shapes or texture differences. So that will help a lot with the classification. So Conv2D it acts like it detects the basic shapes and edges. And then for the batch normalization, it uh, it ensures that the data is clean and stable, and then the dropout is it will prevent overfitting. The flattened and dense layer, which we'll see at the end of the three convolution blocks, it is like a decision maker who will take all the gathered information and decide which tumor type the image belongs to. Then next is the training model. This part it will take quite a while, usually around 5 to 6 minutes if you use the GPU to help. If you use the CPU, it will take quite a long time. So we run around 30 epochs, and so far from there we are able to gain around 91.3%. So the range is usually above 90%. After training the model, I, the reason I wouldn't run the training model because it's too long. So I'll just save and then can load again. So load the training model and then evaluate. So these are the evaluation metrics that we use. First is the test accuracy that is going to generate, which is 91.3%. And then next is the confusion matrix, which is to identify the false positives and the false negatives that are inside our from the training previously. And then we have the classification report consisting of precision, recall, F1 score, and support. And then we have the model accuracy and the model loss. So it will generate this as well. And system evaluation is where we actually test our model whether it is able to detect the image that we give it. So let's say below here we have the typical test cases and the edge test cases. So firstly we have glioma tumor test. So we just put in the file path and then put the function predict image class. Then it will detect whether it is from glioma or not. So the prediction here is glioma tumor and the true class is glioma. So therefore the prediction is correct. Then next is pituitary tumor test. The prediction is pituitary and the true class is pituitary. So far there's no issues identifying glioma and pituitary. Next, if there is no tumor inside the brain, then the true class is no tumor, and then the prediction made by the AI is no tumor, and it's 100%. So next is meningioma. Meningioma true class is the image is meningioma, and the prediction made by the AI is also meningioma. So far for all test cases, typical test cases, the AI model managed to get it right for all. Then next we move on to each test cases, which is pituitary. This one is taken from another website, not inside the dataset, and I imported it into the dataset. It has a different resolution and a different size. So far, it is able to detect without any modifications. I didn't add blur or any high brightness or low brightness. It is able to detect pituitary without any difficulties, 99.99%. And then we have the pituitary high brightness. So this part is where I increase the brightness slightly. There's a slight difference here. And so far, it is able to still detect that this image is under pituitary tumor. So for the low brightness is where it gets dark. I adjusted the image to be a little bit dark too. And so far, also, the AI is able to manage to detect a low brightness image and it still says pituitary. And then next we have blur image. So I actually added a blur effect on the image to see whether the AI model is able to detect, and so far it did as well. So far, all in all of the images the AI model is able to detect successfully. However, let's not forget about the confusion matrix. Is that there are still some false positives and false negatives inside here. So I think that's all from me.
The model show a strong overall performance, achieving the test accuracy of 91.30%. From the graph, we can see that training accuracy steadily increased and reached nearly 99%, while the validation accuracy peaked around 85% and then fluctuated slightly. This indicates that while the model learned and training data very well, there was some overfitting as it didn't recognize quite as strongly to the validation set. The training loss dropped close to zero, but the validation loss remains somewhat inconsistent after the initial drop, which support this conclusion. From the matrix, we can observe that meningioma tumors are often misclassified as no tumor or pituitary, while other classes are predicted more accurately. For instance, 49 meningioma samples were incorrectly labeled as no tumor. In contrast, no tumor and pituitary classes show minimal confusion, which support their higher score in the classification report. So our model have several strengths, which is high overall accuracy in classifying brain tumor from MRI scan. Our model also effectively distinguish among four tumors categories. It's also automatically learn features from MRI image using convolution layer. It also demonstrates the potential of deep learning in medical image analysis. It's also flexible architecture that allows integration with other advanced techniques. Despite its strength, the model exhibits certain limitations. A key issue is the class imbalance, particularly the underperformance in identifying meningioma tumors. This suggests that the model may be biased toward more prevalent classes in the dataset. Additionally, while basic data augmentation was applied, the model may still suffer from overfitting due to limitation variety in the training data. This implementation impact the model generalizability across different patient group and imaging condition.
So, in conclude, we developed a CNN model that classifies brain tumors into four types and achieve 90% of test accuracy. It performed well for glioma, pituitary, and non-tumor classes, but a little bit struggle with meningioma due to class imbalance and visual similarities. For further improvement, we plan to balance the dataset, apply stronger data augmentation, and use pre-trained model like ResNet 50. We also aim to add explainable tool like GradeCam and include tumor segmentation to boost accuracy and clinical reliability. That's all for us. Thank you so much.